So let's look at the first application of Lagrange's theorem. This is proposition 3. Suppose that G is a finite group. G is finite and it has order n, so you know that G has n objects in it. For any element in the group, the order of A has to divide n. Okay? So not only do sizes of subgroups necessarily divide the order of G, so must orders of elements. And the proof is too easy now. By our previous work, we know the order of A is equal to the order of the subgroup, the cyclic subgroup generated by A. We proved that on a few handouts ago in class, actually, back when we were meeting face to face. So the order of A is exactly the same thing as the order of the subgroup, the cyclic subgroup generated by A. But the size of this subgroup has to divide n, but the size of that subgroup is the order. Well, you're done. So it's that easy. And this explains the corollary that I botched before we adjourned when I accidentally put it on the wrong handout. Well, here it is. I claimed in a previous discussion in class that suppose you have a group G and it's finite and it has n objects in it, it has n elements. Then for every element in the group, no matter who you pick, the nth power of that element has to kill it and give the identity. So no matter who you pick, the size of the group, use the size of the group as an exponent, that has to wipe out A and make the identity. Okay? And so continuing, we know by proposition 3, we know that the order of A has to divide n, right? We just did that. Well, if the order of A has to divide n, that means you can write n as a multiple of the order. So write it that way. So n is writable as the order of A times k for some integer. And then we just compute A to the n. So what is A to the n? Well, we just argued that n is order of A times k, so replace it. Use your laws of exponent. That's A to this order, all done to the kth power. But the order of A is by definition, that is the smallest positive integer that kills A. So A to the order of A must be the identity. So you get e to the k, which is e. So you're done. A to the n has to be e. Right? Not so bad. The proofs, please notice, the proofs are very short. Right? The proofs are very short. And finally, here is the most impressive corollary of Lagrange's theorem. We're going to be making a lot of arguments, a lot like this, the rest of the semester. And we'll even be making arguments like this into the fall when we take Math 432, hopefully face to face. And this is a very, very strong theorem that you will learn to appreciate even more once we start talking about isomorphism types, okay? That's coming up in the next unit that we do, okay? But here's a really impressive theorem. Let G be a finite group of a prime order, okay? So you have a group of prime order P, so it could be a group of order 2, a group of order 3, 5, 7, 11, 13, 17, whatever you want, any prime order group. The amazing fact is the group has to be cyclic, okay? So any group of prime order has to be cyclic. This is kind of amazing to me. The proof is very easy, again, if you just use Lagrange and think about it the right way. So here's the proof. Take an element from the group that's not the identity. Now we can do that because the group was prime ordered, and 1 is not a prime. So the group had to be order 2 or order 3 or order 5 and so on. And so it's at least order 2. So it's got to have the identity and somebody else in it. Okay, we'll pick somebody else. Now look at the subgroup that element generates. Okay, that element generates a subgroup, call it H. Now by Lagrange, the size of that subgroup must divide the size of the group, which is a prime. Okay, but primes have only 2 divisors, 1 and P. So the only options for the size of H is the size of H could be 1 or the size of H could be P. Right? But it can't be 1 because H has the identity in it and it has A in it, but A was not the identity. So the size of H being 1 is not possible. Therefore, the size of H has to be P, but that's the size of the mother. So H has to be the whole group. Well, H was a cyclic subgroup generated by A, so therefore G has to be cyclic, and you're done. So it's a very clever proof where you count something and realize that the mother has an order with only 2 divisors, and that very, very, very drastically limits you on what H could be. Very, very, very famous application of Lagrange. So one final word here about Lagrange's theorem before we move on to the next topic. The converse to Lagrange is really, really false. And it's a famous trap for students is to incorrectly apply the converse to Lagrange. So here's what I mean. Let G be a finite group. Lagrange says that if H is any subgroup, then the size of H has to divide the size of G, right? Now, the contrapositive of that says something very strong. The contrapositive would say something like this. If you had a group of order 20, right, there's no way in the world it can have a subgroup of order 8 because 8 is not a divisor of 20, right? So a group of order 20 cannot have a subgroup of order 8. It's impossible, right? But for a group of order 20, that does not mean that it will have a subgroup of order 10 because 10 divides it. That's not what it says, right? 10 divides 20. That does not say there must be a subgroup of order H, of order 10. It's impossible. It doesn't say that at all, right? So Lagrange does not say that if M is a divisor of the order of G, then G will have a subgroup of that order. That's not what it says. That's the false converse. So be very, very careful about this. The converse to Lagrange is false. Just be careful, okay?